All right, so there's kind of a lot in this scatter plot section, so I'm going to go through things fairly quickly. So certainly stop, pause, write things down as you need to, and certainly ask questions if you want more detail or follow up or something like that. But we'll try and touch on everything here as we go. So first of all, the idea is we started with looking at univariate data, one variable data. That's what we're doing with all of the stem plots, dot plots, histograms, all of those box plots, all those kinds of graphs are for univariate data where you have one variable. When you have graphs with one variable and we're describing them, that's where we use CUS, center, unusual point, shape, and spread. Now, in this section, we're going to look at bivariate data. We're going to have two variables and we're looking at the relationship between them. And I don't just mean two lists of numbers. We can take two lists of numbers and make side-by-side box plots. But in this case, these two lists of numbers are related. They are connected in some fashion. When we describe these, we need FUDs. So when we describe scatter plots, we're going to look at form, unusual points, direction, and strength. And I'll go through a little more detail about that in a minute. But the difference between the two is FUDs is for scatter plots. CUS is for those one variable graphs. Dot plots, histograms, stem plots, stuff like that. Okay, so when we have our two variables, one of those variables we call the explanatory variable. That is our x-axis on the graph. And this is what we base our predictions on. This is the variable that we are looking at and measuring to base our predictions on. The response variable is whatever we are trying to predict. So whatever you're trying to predict, that is your y. Whatever you're using to make the predictions, that is your x. One thing we need to be careful of, as we're talking about this whole explanatory response, explain and cause are not the same thing. So for example, the time you spend studying on a test, if that was your x variable, and then our response variable was your score on the test, that there is probably, hopefully, some cause and effect. The amount of time you spend studying actually causes you to improve your score, increase your score. So that would be an example where we do have cause and effect. On the other hand, at certain parts of the year, we would notice that ice cream sales and sunscreen usage tend to change in the same direction. And you might look at that set of data and say, oh, when ice cream sales increase, sunscreen usage increases. But that is not cause and effect. That is just one. We can use one variable to explain the other. But in real life, obviously, what's happening is the weather. When the weather gets warmer, people buy more ice cream, and also people use more sunscreen. It's not that if some ice cream sale boom happens, that's like somehow causing people to want to use more sunscreen. So I already mentioned before FUDs. Let's talk a little bit more about that. For under form, linear is by far the most common thing that we're going to work with, especially this year where we cut out those last two chapters. But if you saw some other trend in the data, if you saw a curve, if you saw some U-shape, something else, form is where we would describe it. But we're almost for sure going to see form on our test this year if we saw a scatter plot. The U on unusual points stands for outliers, but then also influential points, or if you just have unusual clusters of points, this is where we would also mention it. So the U is really to kind of cover anything unusual that's happening. And we'll talk more about outliers versus influential points a little bit later. Direction, generally for us, is either positive or negative, or neither if it's so scattered, or like a U-shaped graph might start negative, but then it changes and it goes back in a positive direction. So the idea with direction is that you have a positive association if your graph's heading up and to the right, meaning as one variable increases, the other variable increases also. We have a negative association if, as one variable increases, the other decreases. And then strength is just how closely the points you have follow whatever form you're working with, which again for us is most likely linear. And generally, they kind of tell us to stick to classified either as strong, moderate, or weak. If your points are really scattered, we might call that weak. If they're super close to a straight line, we might use strong. Otherwise, moderate kind of covers that huge gray area in the middle where, yeah, I can kind of see a trend, but it's not super close to a line necessarily. So if we were to look at this scatter plot and we wanted to describe it, yes, we're using FUDs. When we do CUS, we really need to do each of those as a separate sentence. There isn't a way to put them all together. You could do that here. So I would say the form is linear. There are no unusual points. The direction is positive because we're going up and to the right. And the strength, I would say, is moderate. It's moderately strong. I can see where the trend would be, but they're not super tight close to a line. This would work perfectly fine, get you full credit, and be a great way to describe this scatter plot. With FUDs, you can, as long as you address all these things, you can be a little bit more succinct if you want. If we said the scatter plot has fairly strong, there's my strength, positive, there's my direction, linear form, there's my form, with no unusual points, then I've still hit all four things, but I'm kind of doing it in one sentence. If you prefer that or that works better for you, by all means, go ahead. Okay, we need a more precise way to be able to compute and check strength of a scatter plot too. If they just say describe it, by all means, just eyeball it. But in a lot of cases, we want to be a little bit more precise, and that is where correlation comes into play. So first of all, you need to know that lowercase r and correlation, those are interchangeable. And correlation really does or touches on three things. It tells us the direction based on whether r is positive or negative. It tells us the strength based on the actual decimal we have. And then specifically, we need to remember that it's only telling us the direction and strength of the linear association. If you have curved data, R doesn't really help you tell how curvy it is compared to some curved form. You won't have to worry about that though this year because we cut out those chapters due to our virus talk here, or our virus life here. Couple of things about correlation. Correlation does not have any units on it. It is just a value, and the number itself is telling us what we need to know. Correlation is always between -1 and 1 inclusive, which means it can be exactly -1, or it can be exactly +1, or it can be somewhere in between. A value of r equals 0 means that there is no linear association, or if you're really close there, it means your data is really scattered and there really isn't any sort of a linear trend that we can see or measure. And if you have a value of 1 or -1, that means you have a perfect linear association, that you can write an equation that exactly hits every single data point in your set that you have. I mentioned this on the first screen, but even if correlation is strong, that does not necessarily mean there's cause and effect. It just means that there's a strong relationship between those two variables that we're working with. Now, r squared, first of all, mathematically is the r value squared. Its name is also the coefficient of determination. And the thing that's tricky is, this year especially, I doubt they would ask you this, but this is something that we should have handy. And when we get closer to the test, we'll put together kind of here's a sheet of important things to know. But if you are going to interpret r squared, I don't know what happened to my squared here. R squared is the proportion of variation in the response variable, in y, that is explained by the explanatory variable, x, in the model. That would be how you would interpret the r squared value. If you want to find the correlation, or if you want to find the r squared value, you would take the correlation and double it, or then square it. We're going to use stat calc, and then we want number 8. Stat calc 4 says linreg, but the variables are in the wrong order. We want stat calc 8. So those of you like rhymes, stat calc 8 is great. Use stat calc 4, no more. And we'll dig in and do a little bit of practice with the calculator with a set of data here at the end. A regression line for a set of data has the form y hat equals a plus bx. The y hat, the reason we have the hat on there is to indicate that it is a predicted y value for a certain x value. So y hat is always our predicted. If you ever see a y, that means an actual observed y value. You will need to be able to interpret the slope and the intercept in context. So in general, b is the slope, and that's how much our predicted y value changes as x increases by 1. So this is kind of the generic version I gave you before. For each increase in whatever x is by 1, the predicted, whatever y is, changes by that slope value on average. And the words predicted and on average, those are important. They need to be there. The a value is our y-intercept, and the y-intercept is just the predicted value of y when x is 0, just like it is in a normal graph in algebra. Just be aware that if they did ask you to interpret the y-intercept in with real data in a real context sometimes doesn't make sense. You might end up with a negative value for something that can't be negative, and that can happen just because where our data actually is living is nowhere near where the y-intercept would be, and a value of 0 just doesn't make much practical sense. But if you are going to interpret y-intercept, there are some cases where it makes complete sense to talk about the y-intercept. The y-intercept is the predicted y value when x is 0. So there's kind of two different ways that you might need to write the regression equation. One is if you have the data. If you have the data, enter it into the calculator. So stat enter, and then we're going to put numbers in list 1 and numbers in list 2. And we're going to get the equation of the regression line using statcalc8. So here's a set of computer output, or not computer, here's a set of, like, this is what your calculator might spit out. If this is what you were looking at and you needed to write the regression equation, we would write y hat, we put the a value first, that's the y-intercept, plus, then we take our slope times x. If they were to give you an equation, they might write it this way. Sometimes they'll also substitute the variables in. This data has to do with arm length versus height. In fact, we're going to work with this data a little bit later. So sometimes on the AP test, they'll actually put in there the variable hat, and instead of x, they'll actually put the x variable. Not a huge deal. I just wanted to remind you or tell you or show you so that it doesn't throw you off if it does happen. So if this was our output for when we were looking at the arm span or the arm length for people versus their height, if you were going to interpret the slope, which is 0.789, here's how I would write it. For each increase in arm length, because that's our x, by 1, the predicted height, which is our y, changes by 0.789 centimeters on average. And you must have those words predicted and on average when you're interpreting. If we were going to interpret the y-intercept, we would say the predicted height for someone with an arm length of 0 is 37.18 because that is what the y-intercept is. But this is one of those scenarios where really I don't know that that has much practical meaning in the real world. Now, that was if you have the data, we can use the calculator. If you don't have the data, where you can just put both lists of numbers in and run statcalc8, then they will probably give you the correlation, the mean of the two lists that your variables are, as well as the standard deviation of those lists. And in real life, this happens sometimes if you have massive sets of data. Rather than have to have somebody type in like 1,000 x values and 1,000 y values, it's a lot easier for a computer to just crunch these out quick, and then they would give those to you. And here would be our formulas. You have to find the slope first, because we actually need the slope when we're calculating the y-intercept. But you're going to take the correlation times the standard deviation of y on top over the standard deviation of x on the bottom, crunch that out and get your b. Then to get the y-intercept, it's going to be the mean of the y list minus the slope you just calculated times the mean of the x list. And again, they would have to give you these values. And these formulas, I mean, this test is open notes anyway, but they are actually on the formula sheet, the official formula sheet, so you do not need to memorize them. Just make sure you know where to find them and have them handy. Okay, so when we are using a regression line, we're finding some predicted y values, and then we have some actual y values. One of the things we will look at are residuals. A residual, I mean, the word residual kind of means like leftover or extra or excess. For us, the residuals are the actual observed y value minus our predicted y value. We're measuring how far off that prediction was from what the actual y value was. When you're making a scatter plot and a regression line, just make sure you know which is which. Y hat is the predicted. Y is the actual observed y value. And when you're looking at a graph, you should know that a positive residual means your y value is actually larger than your y hat value. So here's an example with just 3 points. So if we're looking at those 3 points in a scatter plot and this regression line is running through, by the way, the regression line we use is called a least squares regression line. We'll talk a little bit more about that in a second. The residual is how far off this actual y is from the predicted y, which is the points of this line. These are all predicted values. So the positive residual would mean our actual y is larger than our y hat. So this point would have a positive residual because the actual y is bigger than the predicted y. These 2 points, the actual y value is lower than the predicted y value. So you would have a negative residual for these. When you do one of these least squares regression lines, when we run StatCalc8 on our calculator and get that equation, the mean of all of the residuals that are created from all of your points is always 0. That's a fact that's always true for this kind of a regression line. So the least squares regression model, which is the kind that we use, the reason that becomes our best fit line, or the way that our calculator is determining that, yes, this is the one line that best fits that data, is it's taking all of these distances, and as we just talked about, some of these residuals are negative, some of them are positive. It squares all those residuals so they're all positive values, and then it adds them all up. And that's kind of a way of measuring an overall measurement of how far off were all of these points from the lines where we potentially could have used. And the least squares regression line minimizes that total. One other fact that they explicitly mention, so I want to make sure I tell you, is that the least squares regression model, the type of line we use, always passes through this point, the point x bar comma y bar, for any set of scatter plot data. Now, if you ever asked to find the residual for a single data point, we'll talk a little bit later about how you can get all of the residuals and look at that list of residuals. But if you ever need the residual for a single data point, you would need to plug in the x coordinate of the point you're looking for into your equation, which will give you the y hat value. Then you take the y, so we started with some point, maybe the point 3 comma 5. Now you would take the y coordinate, the 5, and you would subtract the y value you got when you plugged that x into your equation. So that's if you have to find a residual for a single data point. And we'll look at an example here a little bit later. So a residual plot, instead of talking about a single residual, a residual plot is a scatter plot of all of the residuals as the y variable versus the explanatory variable as your x. So you're taking the original x values with your residuals as your y. Or there have been a few questions they've thrown at students in the past where instead of the actual x coordinates, they use the predicted y values as the x versus the residuals. That's the less likely way to do it, especially if they have you do it, but that's also a possibility where you're looking at the residuals versus the predicted y's. Our calculator automatically finds and stores the residuals for us every time we calculate linear regression. Every time you do StatCalc8, the calculator recalculates the residuals. You just need to know where to access them. Which means if you're working with a scatter plot, if you get a scatter plot on one of those two questions, put in your data and run linreg, run that StatCalc8 with that new set of data, so that if you do need to use the residuals, the calculator has the right residuals stored in there. The name of the list is called Resid. It's under second stat, and you should see it might not be number 7 if you have other lists in there, but it will be under that second stat menu. And I'll walk you through a practice one in a little bit here. When you make your residual plot, you're going to see a scatter plot looking thing. It's going to have a line running through the middle that represents y equals 0. If all is well with our regression line, then the pattern in the residual plot should just be an unstructured band of points. So just be a scattered set of points that are centered around 0. So if you saw this as your residual plot, the way we would interpret or describe what that's showing us about the original data is this. We would say, since the residuals are scattered with no curve, a linear model is appropriate for the data. That's one of the main ways we use residual plots, is to decide if a linear model is the correct model for our original data. On the other hand, if you see something like this in the residual plot, there's clearly a curve. So we would say, since there's a clear curve in the residuals, a linear model would not be appropriate for the original data. So let's type some numbers in. You might want to pause here, go into Stat Enter, and let's type these numbers in a list if you want to follow along. I guess you can just watch if you want, but I'm going to put these in. Okay, so if we wanted to make a scatter plot to look at or to sketch, we're going to go to second y equals, and hit Enter. I do not want a box plot. I want to choose that first graph, a scatter plot. And right now I am doing a true scatter plot. So I should do List one as my x's, list one as my y's, and clear out of here. Now I can do zoom 9, and boom, there's my scatter plot. That might look familiar. We looked at this data a little bit earlier, or at least, yeah, I think it was this data in one of the examples I had. Now, the only time we are going to change this is if we're making a residual plot, or if they ask you to make a residual plot. In this case, we want to change the y list to be resid, but we can't do it yet because I just typed those numbers in there. If I am going to ever use resid, I need to do stat calc 8 with list 1 and list 2, leave the frequency list blank, and go down to and hit enter. Now, if your calculator does not go to that menu, you're just going to do linreg, and you're going to type in second 1, comma, second 2, and the comma button is right there underneath sign. And then you'll hit enter. So now, first of all, here's our equation. There's our r squared value and our r value if we needed them. If yours don't show up, you need to go to second 0 for catalog, and we want to go all the way down to the D's to diagnostic on. Don't do off, we want it on. Now if you hit enter and you hit enter one more time, now if you do linreg, those values should show up. If they were already showing up, then obviously you don't need to do anything. So now if I go to second y equals, and I go in here and I want to make a residual plot, I'm going to put my cursor on the y list, go to second stat, and I'm going to choose resid. So now it's going to graph the original x's with the residuals. Clear out of here, and now if I zoom 9, there would be my residual plot for this data. There is a scattered set of points where there's no clear curve, so here I would say linear model is appropriate. And you can eyeball that from the original scatter plot too, but residual plots are often a way to confirm that, or if it is hard to tell, it's a way to double check, and sometimes they'll just flat out ask you to make a residual plot. Okay, and I already talked through it, but those are the steps. So, our regression equation for that data was this. Let's say they asked you to find the predicted y value for an arm span of 166. So arm span is an x value. So if we wanted to find the predicted y value, what we would be doing is plugging in 166 for x, and then 168.54 would be my predicted y value. This would be a y hat value. So that's how you would find a single predicted y value. Let's say they asked you to find a residual for an arm span of 66. Well, if you hadn't done that first part yet, we'd still have to do that first. So you'd have to plug in 166, get your y hat value. But now to get the actual residual, we need to go to our data. When my x was 166, my actual y value was 165. So to get the residual, I need to do the actual y, 165, minus my y hat value, minus the 168.54. My residual for this data would be negative 3.54. Okay, then just the last couple of things as far as scatter plots. First, an outlier. You can kind of eyeball them just based on what you see in your scatter plot, especially if we look at that original data. This one does not have any outliers. But an outlier, the way we would describe it is, it's a point that doesn't follow the trend of the data. Or if you want to literally pull this apart, it is a point that lies outside of the rest of the trend. So if where my cursor is over here on the graph, if I had a point there, that would be an outlier. It does not follow the trend of the rest of these if it's down here. If you're looking at a residual plot, outliers will have large residuals because here's where my point would be, but my line would be predicting it should be somewhere up here, and that distance between those would be pretty large. A high leverage point is something a little bit different. A high leverage point in regression has a substantially larger x value or smaller x value than the other points. So here's a scatter plot. This would be an example where this point here would be a high leverage point. It's a high leverage point because its x value is much larger than the rest of these. And the catch with a high leverage point is high leverage points tend to pull this regression line so that it's somewhat close to that point, and it makes it seem like maybe this trend is stronger than it is. So high leverage point is one that has an X value that's much larger, or it could be over here, so that's much smaller than the rest of your data. Influential point is a little bit more general than outliers or high leverage. Outliers and high leverage have specific idea behind where they are. Outliers don't follow the trend, so this point down here would be an outlier because it doesn't follow the trend of the rest of these points. This is a high leverage point and not an outlier. It's not an outlier because it follows the trend, it's just further away. But it's a high leverage point because the X value is so much larger than the rest of these points. An influential point is any point that if you removed it would change the slope, the y-intercept, or correlation substantially. If it changes that relationship quite a bit, that would be an influential point. And the bottom line is that influential points with high leverage, which is what this would be, can be tough to see in a residual plot because they tend to pull the line toward it. When we're going to crunch out these numbers, the best fit line is trying to factor this in, and since it's so much further away, it kind of tends to steer the line over here. So if we just use the residual plot, you can't really see that it's different than the rest of these. We really do need to look at the X distance for influential points. For high leverage points. The bottom line is both outliers and high leverage points tend to be influential. With outliers, if you removed them, that's going to make your correlation go up. It's going to be a much stronger set of data because you don't have this point that's bucking the trend in the data anymore. High leverage points, it almost works the opposite. If I remove this point, my correlation is going to tend to go down because now a point that was far away, which kind of makes it seem like, hey, this trend is right on. Look at it, it's still held this far away. If you remove it, now your R is only measured for these points, and that's generally going to tend to make the correlation go down. So influential point just means if those values change noticeably at all, then it's influential. They might go up or they might go down depending on the particular point. Then one more term to bring up here is the term extrapolation. Extrapolation is predicting a response value using a value for the explanatory variable that is beyond the interval. So what that means, if I'm looking at this scatter plot on my calculator, a lot of times we want to take the data we have right now and kind of predict the future. That's extrapolation. If these are my data points and I decide, you know what, I want to find out what's going to happen for an X way over here, well, that's outside the range of my data. I'm extrapolating and assuming that this trend is going to hold. And the bottom line with extrapolation is that it's less reliable the further we get from the set of points. I could maybe go a little bit bigger in the X direction and have the model still hold fairly close. But the farther away you get with your X values, the less reliable that extrapolation is. The absolute last thing we're going to look at here for Chapter 3 is what if we have computer output? And because of the chapters we skipped, we actually can skip a bunch of this computer output, including this R-SQ, which does stand for R squared, but with ADJ, we're not going to bother. The ones you need to know, though, are the R-SQ, that is R squared, which means if they ask you for correlation, you would take that value and take the square root. The only catch is if you're solving for R from an R squared, we need to worry about both the positive and the negative version. So in this problem, we would need to look at the slope. The slope and the R value always have the same sign. So let's come back to that in a second. This S, I doubt they would ask about, but it is the standard deviation of the residuals. I just don't think they'll ask about it. There's not much that we actually do with it other than answer a specific question. But if they ask you for what is the standard deviation of the residuals, you just pull that S value. The two most likely things that you would have to use are these other two. Now, stands for coefficient. One of these two lines, it's not always the top line, but one of these two lines will be labeled constant. The constant coefficient, that is our y-intercept always. The other line is going to be labeled with some variable from the problem. So this is from a problem about non-exercise activity. That's what NEA stands for. But it doesn't matter. What you need to know is the line that's not the constant, whatever coefficient is there, that is our slope in the problem. So the most likely thing you'd have to do from computer output would be either to find R squared, which you have right there, or write the equation of the least squares regression line, and then we're just filling in y hat equals my y-intercept, the constant coefficient, plus the slope, which here the slope is negative, times x. If they asked you for correlation here, it is true that r squared is 0.606, if we're going as a decimal, which means that r is the square root of that. But we don't know if it's the positive or the negative version. It depends on the other information of the problem. Well, if your slope is negative, r has to be negative. The value for r has to match the direction of the problem, which is what slope is. So here our r would be negative, and then the square root of 0.606 is 0.778.